The IPCC Air 4 concluded that climate change will have significant impact on many aspects of biodiversity. Air 5 and subsequent reports such as SR 1.5, SRCCL, and SROCC all discuss the climate change impacts on ecosystems from a more realistic point of view. Climate change is already having a dramatic effect on many ecosystems, leading to questions about what the future will bring. In recent years, plant and animal populations have changed much more quickly and drastically than anticipated, and there is evidence that the pace of the change is accelerating. In this section, we start with looking at the latest scientific knowledge, how the climate change is actually being observed, and how the climate of the Earth is projected to evolve in the future. First, greenhouse gases. Please look at the left panel, which WMO presented in its status report of the global climate for 2020. It shows the concentration of CO2 has continued to increase since 1985 through 2019 and 2020. Its latest average has already exceeded 410 ppm, which is about 50% higher than before the Industrial Revolution. Importantly here, more than 30% of the anthropogenic CO2 have been absorbed by the ocean and lead to acidification. Temperature. The middle panel shows the global mean temperature change from 1850. As you see, temperature has also shown a robust warming that occurred from the early 20th century, particularly from the 1970s. WMO announced that 6 years from 2015 to 2020 was the 6th warmest years on record. Also, over the Pacific Islands, the 2020 annual average was the 4th warmest years on record. Increase of surface temperature is a trend across the globe. However, we should know that the warming trend is not uniform, as shown in the right panel. Temperature changes are so different by location. By and large, most land regions are warming faster, the Arctic region in particular, while most ocean regions are warming at a slower rate. Precipitation. A clear trend in observation of precipitation is the increase of precipitation over mid-latitude land areas, particularly in the northern hemisphere. You can find it in the left panel by darker green prevailing over North America and Eurasia. However, as compared with temperature, there's less confidence in identifying the change in precipitation. This is mainly because of the sparsity and less quality of data. Sea level. An increasing trend is clear across the globe. Mostly, sea level rise is caused by a combination of thermal expansion of ocean water and melting of polar ice caps and glaciers. The middle panel shows that the global mean sea level has been continually rising since 1993 at an average of 3.42 millimeter per year. During 2006 to 2015, it made the highest record over the last century. However, regional differences and temporal changes of this trend need to be considered, which is clearly shown in the panel on the right. Lastly, let me emphasize that the recent enhanced measurements all tell us that a combination of glacial mass loss and ocean thermal expansion from warming is playing an ever greater role and now explains about 75% of the observed sea level rise. Ocean temperature. Globally, the ocean has continued to warm over the past century as it absorbed more than 90% of the excess heat which is produced as climate change warms the Earth. It is particularly clear since 1970, as we see in the bottom left chart panel. The annual global mean in 2020 was plus 0.31 degrees above the 1981 to 2010 average, making it the third highest since 1891. In the western tropical Pacific, observations also clearly indicate the ocean surface warming. However, the trends are difficult to define in time and space, as shown in the panel on the right, mainly due to the internal variability of ocean, such as ENSO and IPO. Acidification. Seawater is becoming more acidic across entire oceans. You can see this in a set of three panels on the right. The top panel shows the increase of CO2 concentration and the decrease of pH in reverse proportions since 1990s. Meantime, two charts below give us a global view of the pH changes from 1870s to 1990s. From these charts, we note first that acidification proceeded so quickly and globally over this 100 and some years. Also, we note there's a large difference in acidification from place to place. It was significant over the tropical ocean, west coast, and southern ocean. Now we move on to projections. Projections of climate change due to greenhouse gas increase are made under the four emission scenarios, or representative concentration pathways (RCPs). They are shown in the top right panel, namely RCPs 2.6, 4.5, 6.0, and 8.5. Each index represents radiative forcing. The larger the index, the more the Earth's surface is warmed. Temperature. Please look at the panel below that shows the temperature changes for the four scenarios during the 21st century. Clearly, there are large differences. It will be 2 degrees or more at the end of the century between RCPs 8.5 and 2.6. The bottom panel shows the projected temperature increase in the late 21st century under the highest emission scenario. As you see, it illustrates a rather different world than today, 4 degrees or higher in most of the land areas. The two maps on the right give us a regional view for the middle of the century on the left and the later part on the right. Temperature will be a bit lower than the land areas, but about 3 degrees or more higher than today. What I should emphasize here also is that climate models suggest there is a growing risk of extremely hot temperatures, heat waves in other words, with higher frequencies and for longer periods as global warming proceeds. Precipitation. Precipitation has a unique characteristic as it represents opposite changing trends over time and space. Roughly, the contrast will become more significant between dry region and wet regions, as well as dry season and rainy season. We can see it clearly in the bottom left panel. For the Pacific region, the two maps on the right compare the projections for 2 seasons. During November to April, on the left, rainfall will increase along the equator and decrease at the northeastern edge of the SPCZ region. During May to October on the right, Rainfall will increase along the equator and the northwest area and slightly increase or decrease south of the equator. Sea level. Sea level is projected to continue to rise through the 21st century and even beyond for all scenarios as shown in the top right panel. As discussed in the observation part, we should consider that sea level rise is accelerating at faster than expected rate. Such a large and quick rise in the sea level could lead to an increased frequency of extreme sea level events. This is schematically shown in the bottom right panel. Many low-lying coastal areas and small islands could be exposed to historical centenary events, at least on an annual basis, by the middle of the century under all emission scenarios. Ocean temperature. The ocean will continue to warm through the 21st century. This is one of the key messages from IPCC and is represented in the top right chart. It compares the future change of SST under RCP 8.5 and 2.6. For 8.5, the global mean SST will be about 2.6 degrees at the end of the century. Along with the SST increase, it is worth noting that such warming will lead to occurrence of extreme heat conditions across the ocean. The bottom right chart shows the projected change in frequency of marine heat waves from the pre-industrial period. As you see here, the increase in the frequency of marine heat waves is a global trend, and the largest increase are found in the tropical ocean, especially over the western Pacific. Acidification. Observed trend of ocean acidification will continue all through this century, along with the further uptake of carbon by the ocean. It is clearly shown in the bottom middle panel. Under RCP 8.5, the ocean pH will continue to decrease and will reach around 7.8 at the end of this century. This is about 0.3 units lower than the present value. The panel on the left shows its future distribution. It is almost amazing that entire ocean will become more acidic over the 21st century. Under the high emission scenario, the equatorial Pacific will experience highly acidic conditions that are very marginal for coral and coral reefs. Tropical cyclones. Regarding tropical cyclones, simulation capabilities of global models are still challenging. However, a recent study on the future status under 2 degrees warming projected several important features. First, frequency of all cyclones will decrease. Second, proportion of category 4 to 5 cyclones will increase. Third, average intensity will increase. And lastly, cyclone precipitation will increase. Although there are different characteristics between basins, tendencies are similar for all the 7 basins, including northwestern and southwestern Pacific. In a word, tropical cyclones will be less frequent but more severe. Further, it should be noted that the study emphasized with high confidence that sea level rise will lead to higher storm inundation levels in conjunction with those changes of TC activities. Although there may be a slight reduction in the overall frequency, an increased proportion of the most intense cyclones and associated heavy rainfalls means most locations in the Pacific will have a higher chance of being exposed to more serious impact of tropical cyclones such as intense storm surges, swells, and floodings. Obviously, the richness of biodiversity of the Pacific Islands is globally recognized and is also of huge importance for global biodiversity. At the same time, Pacific Islanders enjoy enormous amount of services from the various ecosystems of terrestrial, freshwater, marine, and coastal domains. However, island ecosystems of the Pacific are very fragile because species populations are small, localized, and highly specialized. Corals, for example. The map of the slide suggests quite a few coral reefs in our region are under significant threat levels. Meantime, due to their geographic features, many islands of the Pacific are susceptible to changing climates, including the higher temperatures of the air and the ocean, sea level rise, acidification, and more intense storms. All these inevitably affect the terrestrial, freshwater, marine, and coastal ecosystems of the Pacific. We will examine those impacts in the next slides. Roughly speaking, terrestrial ecosystems in the Pacific Islands are divided between low islands such as atolls and high islands such as volcanic and subcontinental. Warming at high elevation could provoke invasive species problems and alter the distribution of native species. Loss of forest could seriously affect the richness and abundance in terrestrial ecosystems. Change in precipitation patterns may lead to increased coastal erosion, decrease in coastal water quality, and changes in terrestrial species distribution. While the change in precipitation and temperature is a major threat to terrestrial ecosystems, low islands ecosystems lack the elevation gradient and land area for species to adjust their distribution in response to climate change effects. Atoll species are at further risk due to habitat loss from sea level rise. Freshwater ecosystems are vital for ecosystem services globally, but they are quite sensitive to the impacts of environmental change. One of the most important and major impacts to be caused by climate change will be on freshwater flow regime. In most of the cases, climate change together with other human-induced stressors will cause much damage to freshwater ecosystems. For the Pacific marine and coastal ecosystems, changes in sea surface temperature, sea level rise, ocean acidification, precipitation, and storm intensities are the main factors of climate change impact. Sea level rise may already be causing erosion and inundation and makes mangroves to shift landward in island regions. It is most serious if there is no path for landward migration. Shift in rainfall pattern could alter the freshwater flows to the habitat, changing the salinity and mangrove composition and structure. Mangrove forests are seriously affected by intense storms, but we should also focus our eyes on the important role as a natural defense against the cyclones. Climate change is already impacting coral reefs through bleaching. Increased seawater temperatures are correlated with increased frequency and intensity of mass coral bleaching events and associated mortality in the region. Increase of seawater temperature is also linked with El Niño, which is projected to be more frequent and intense along with climate change. For seagrass meadows, Sea level rise and increase of seawater temperature pose main threats to their species distribution and growth rate. Over the past decades, there have been several global die-off events. Climate change and additional anthropogenic factors such as runoff of sediments and land-based pollution will be resulting in increasing losses of the ecosystem services from seagrass. The intent of the slide is to make a brief review of the climate change impacts on ecosystems encompassing all the chains including of the ecosystem services. Climate change impacts on ecosystems bear deep influence on a wide range of human activities. The diagram of the slide gives a whole picture of climate change impacts on Pacific ecosystems. Please note it includes some flows that were not covered in the earlier slides of my presentation. I will avoid discussion on details of each of the flows, but would like you to first draw your eyes on the set of main variables of climate change, specifically change of CO2, temperatures, precipitation, SST, acidification, and sea level rise on the top of the panel, and then the various impacts in the middle part of the diagram, particularly change of abundance and distribution of ecosystems, and lastly the relevant sectors in the bottom, which are affected through the change of ecosystem services. Human activities including the primary industries such as agriculture and fishery, social and civil life, tourism, and cultural activity, and even the disaster risk reduction, all these key sectors of the Pacific region receive the benefit of ecosystem services. So I would stress that when we discuss the climate change impact on ecosystems, it will be essential for us to look at it from a broader perspective, including this critical aspect of ecosystem services and continuation of its provision.